Hi guys, welcome to the second lecture on analysis of algorithms. So we talked about looking at how things grow and how we only really cared about the dominant term in the functions that we're looking at. So we're going to make this a little more formal. Well, not really formal, but we're going to use a notation called big O notation. So we know that the coefficients and the lower order terms don't really matter as n increases. They just sort of become unimportant. So what we say in this case, in the case of the one that we're looking at before, we're going to say that the algorithm is order n squared. So we're just going to throw the constants out. We're going to throw the lower order terms out. We're just going to say it's big O of n squared. And this is called big O notation. And again, you'll formally see this when you take algorithms, but it's basically just sort of like it's the asymptotic complexity of the algorithm as it increases, right? So you throw away all the constants, you throw away all the smaller, weaker terms, and you just keep the ones that really affect the growth, okay? And usually there's only going to be like one of those, okay? So there are various big O categories. Two algorithms in the same category are generally considered to have the same efficiency, but that doesn't mean that they actually have equal growth functions or behave exactly the same for all values of n. So some algorithms may, you may have two n squared algorithms. One may have smaller coefficients, or that may work better on smaller data sets or under certain circumstances. It doesn't mean that they always behave exactly correctly. It just means that comparatively speaking, they behave about the same. So if you're picking between algorithms and for example, let's say you got to do sorting. And you have two algorithms, and one of them is n squared, and one of them is order n. And you say, well, which one should I pick? It doesn't really matter in general what the constants are, the extra terms are. The n squared algorithm is almost always going to be worse than the n algorithm, right? So you have to understand this, that we're looking at really is as the problem gets big. We're not really concerned with small problems. Small problems don't matter, right? You can use horrible sorts, horrible searches on very small problems, and you'll never notice. The computer is just so fast. But as the problems get much larger and the size of n gets really big, then you're going to need to know about these things. You're going to need to be more efficient, which anything that's non-trivial is going to be the case, right? You can get by with writing, little web apps and things, but even those, a lot of times you'll see, really terrible performance sometimes from a web application. And a lot of times it's the choice of the algorithm that someone made, and they just didn't understand this, and they picked some terrible algorithm, and it doesn't work very well, and they don't know why. But this is why, because we really have to think about these things. When you run small test cases, a lot of times it won't really make a difference to you. But when you move to production systems where you're working with lots of data and things, these sorts of things will really matter. All right, so we have some different big O categories here we can look at. We have big O of 1. Big O of 1 means it's constant. It doesn't matter what n is. It always takes the same amount of time, okay? So what's a function that's, let's say I'm adding 1 to n. It doesn't matter what n is. If I add 1 to n, it's always the same amount of time, regardless of what n is, right? So log n, order log n is what we say it's logarithmic, right? Means it looks like a logarithmic function. So notice that we just write log. Usually when you write log, there's a base. Maybe log is base 10, or it could be base 2. A lot of times in computer science, it's going to be base 2. It actually doesn't matter, because if you go back and you think about logarithms, you realize that you can rewrite any base in another base as a constant times the logarithm in the base that you want to be in. So it's actually, it really doesn't matter. But again, it's just another case of a constant times something. So we don't usually write like, big O log base 2. We just write big O log, and we say that that's logarithmic. So we have linear, which is, it's linear. You know what a line is. We have n log n, which amazingly is very popular. So n log n, so I know you guys have seen like merge sort, right? So merge sort, you split things up and then you merge them, right? As you go back up, you split your array up into little pieces, and then you merge the little pieces as you go back up. So if you think about merge sort, as we split things up, how many pieces do we split them up into? How many levels are there? So if you split things in two every time, there's going to be log base 2 levels, right? So at every level, we need to sort in things, right? So the total complexity of a merge sort is in things sorted times log n levels is in log n. So merge sort is an n log n sort, okay? We look at something like n squared, it's quadratic. Quadratic would be something like bubble sort. If you think about bubble sort, you take the biggest one, you push it up to the top, you take the next biggest one, you push it up to the top, you take the next biggest one, you push it up to the top. If you think about how many compares you have to do with that, it's its own order n squared. That's why something like bubble sort is typically terrible for a sort. You should never use bubble sort for anything. You should always use merge sort or quick sort. There's actually one better sort called radix sort, but it only works in certain circumstances. It's an order n algorithm, but it only works in certain circumstances. Bubble sort for very small numbers of n can be better than merge sort because the overhead of it is smaller. But as n gets large, merge sort and quick sort are always going to be better, right? And for small numbers of n, that overhead from using merge is not really going to be noticeable on your PC, right? So you basically should pretty much always use merge or quick. Take your pick. You'll see this in algorithms again. Cubic, there's a lot of cubic algorithms, but I'd have to think of one that was particularly bad. And then the last one is exponential. So exponential is 2 to the n or any number to the n. It actually doesn't matter what number that is to the n. But 2 to the n is an exponential function. And that's a really, really bad one. So if you look at these examples, you see that the growth functions, so there's like 2 to the n plus 18n squared plus 3n. That 2 to the n is always going to grow enormously fast, right? It's going to grow ridiculously fast. So those n squared terms, or actually any polynomial term, it doesn't even matter what it is. It could be, into the 2 millionth. It doesn't make any difference. Eventually that 2n is going to grow much faster than that n to the whatever. So the exponential is dominated by the exponential term, and so we call it exponential. All right. So you might think that faster processes would make efficient algorithms less important, but actually, that's not actually the case. So a faster CPU helps, but it's not really relative to the dominant term. So let's think about an exponential algorithm. Let's say we picked an exponential algorithm because for some problems, that's all that exists, right, is exponential algorithm. So let's say we pick an exponential algorithm, 2 to the n, all right? And let's say our processor speed doubles. Double is pretty good, right? I mean, how often does Intel come out with a version of a processor that doubles? Doubling is pretty good. So let's say we double the speed of the processor. How much can we increase in if we've doubled the speed of the processor and we're using an exponential algorithm? It's 1, right? Because 2 to the n plus 1 is twice as big as 2 to the n. So if we could solve a problem in a week with processor 1 and we bought processor 2, we could solve an n plus 1 size. We could add one more element to the problem and solve it on this twice as fast processor, right? So the CPU helps, but the order of the algorithm is still important, right? The amount that we can add to the algorithm, or the amount of n that we can add as the CPU increases in speed, is really not that much relative to the size of the algorithm. So the algorithm is still, the time complexity of the algorithm is still going to be the dominant factor. The CPU speed is just a constant. We talked about the constants. The CPU speed is just a constant in there. It really doesn't have a huge effect on the performance as n goes to something really large, okay? And relatively speaking, the better performing algorithms, the smaller time complexity algorithms are always going to perform better. It doesn't matter what the CPU speed is. And the CPU speed does matter. I mean, the CPU speed does not matter because increasing the CPU speed just lets us increase n in a lot of cases by a very small amount. Okay? So we can look at some functions and sort of get a feeling for this. Here is all the functions that we've been talking about. We got 2 to the n cubed, n squared, n log r, n, and then log n. And you see that these things, even at size 25, diverge a lot, right? For input size n, the time complexity diverges a lot for these different. You see that the exponential one just goes through the roof, right? So what's interesting here, though, if you look at it, you'll see that actually for this very small value of n, that the input size around 5, that actually n cubed is still worse than 2 to the n, right? Even though we know that 2 to the n eventually is just going to be ridiculously bad, for very small sizes of n cubed is better. But we don't care about those things. Those things don't matter to us when we're picking an algorithm. We don't solve size 5 problems. It's not interesting, right? Who cares? You're going to sort 5 elements in an array. We don't care. It doesn't matter. What we're really looking for is when n gets really large, so larger size problems. So again, when you look at that for much larger sizes, we see now that 2 to the n has just gotten enormous. That these other things are growing like fairly relatively slowly. The 2 to the n looks like it goes just straight up, right? Even n cubed looks pretty big, but 2 to the n goes straight up. N squared is pretty bad. And these others that are down here, they look fairly flat, comparatively speaking, even though we know that n log n is not going to be as good as n. They look fairly flat down here because compared to the others, the difference is so much smaller compared to say the exponential. So this is how growth functions. This is to sort of give you an idea of how these different growth functions look. If you've had calculus, again, you should probably know all this stuff. But algorithmic complexity is really important. And when you're looking at all the algorithms that we're going to look at in the future, you really need to think to yourself, and we'll discuss what's the complexity of, say, adding something to the data structure, finding something in the data structure, removing something from the data structure. All of those have a complexity, and depending on what you're going to do, that may have an effect on which data structure you pick, right? And we'll see more of this as we go into data structures. All right, so now we're going to look at analyzing loop execution. So how do we look at a piece of code, and how do we go from a piece of code to this complexity measure? So we need to first look at the order of the body of the loop and then multiply that by the number of times the loop is going to execute. So let's look at this example function here, and we're going to see something like count equals 0, count less than n, count plus plus, and then inside of the loop is order 1 steps. Order 1 is constant, right? So it doesn't matter what n is, the things that we're doing inside that loop are going to take the same amount of time. So we have something that's a constant times, and the loop is going to iterate n times. So if we're going to do n loop iterations and we're going to do something that's constant, it's basically just n times the constant, right? Which is big O of n efficiency. So we throw out the constant. We don't care what that O1 term actually is in there. We just toss that out and we say this is big O of n efficiency. Okay? So that's for a single loop. So now when we look at well, this is a slightly more complicated single loop. So that was a simple for loop. Here we're looking at a while loop, and we have while count less than n. So we're still bounding based on, we're starting at 1, we're going up to n. But count is multiplied times 2, right? So if you think about what that looks like, what kind of function is that? That's not add 1 to it, add 1 to it, add 1 to it. This is multiplying by 2, so we're basically exponentiating, right? So the first one is, so we're multiplying by 2 every time. So the sequence is going to go 1, 2, 4, 8, 16, 32, 64, 128, 256, etc., etc., etc. So the count, which is the thing that's controlling it, is going to go up exponentially. So the number of times that we're going to execute this, the number of times that count can be incremented like this, is going to be log base 2 of n times. Because if you think about this, this is basically just 2 to the n, right? Because we're starting at 1, 1 is 2 to the 0. We're multiplying that times 2. So the first loop is going to be 2 to the 1. It's going to be 2 to the second, 2 to the third. So the question is, what is the largest number of counts such that count is less than n? And if you think about it, that's just a discrete log of n base 2, right? So the order of this loop is big O of log n because the count is incremented exponentially. And so the number of steps and then the loop body itself is only big O of 1. So it's log n loop iterations, log n base 2. And again, we're going to throw that base out because we could actually rewrite this as log base 10 or log base whatever. But it's going to be log base n times that we're going to iterate through the loop. And then we're going to do order 1 steps, which is a constant. So that's just big O of log n. Okay? So it's a little bit more abstract, a little bit harder to look at and get in your head around it. But if you think about how the count goes up, you'll see that it's actually just they're all powers of 2, right? All right. Look at something a little more complicated here. So let's say we have nested loops. So nested loops, we do pretty much the same way, but we have to look at the complexity of the inner loop first. So the inner loop, so in the previous ones, the thing that was in the loop, the complexity of it was always order 1. But if the inside thing is a loop, then the order is not order 1 anymore, right? Now it's order something else. So, but inside of that loop is order 1. So what we do is we estimate the order of the inner loop. So it's going to execute 0 to n times. And what executes inside of it is order 1. So that's going to be k times n, right? And then the outer loop is going to also execute n times. So that's k times n, which is kn squared, which is just big O of n squared, right? Does that make sense? So an interesting thing to think about here is, well, what if, so it's a common case that the inner loop would increment or loop, instead of being a function of n, it would be a function of count. So it would be something like int count 2 equals 0, count 2 less than count 2 plus plus. So the question in that case would be, what would be the order of the loop in that case, right? It's a slightly more complicated case. So the inside would still be big O of 1, right? It's constant. The outer loop, the first one would iterate 1 time, the second would iterate 2 times, the next one would iterate 3 times, 4 times. On average, it would iterate n over 2 times, right? The average number of iterations would be n over 2 times, right? So that would be n over 2 times k, which is the big O1. So it'd be k times n over 2, which is really just k times n, right? And then the outer loop would still execute n times. So it would be k times n, which is just n squared, right? So even though that inner loop would be less than n times, it would iterate less than n times, it's still iterating a function of n times, and it's still big O of n. The inner loop is still big O of n. We throw out those constants, it's big O of n, the outer loop is big O of n, and it's n squared. So there's a lot of different ways that you could write these loops, and they would all be n squared. You have to think about these things a little bit. Look at how the inner loop is changing, how many times is it going to count, how many times on average is it going to run, and then look at the outer loop, how many times is it going to run, and then you can estimate the complexity of your code, okay? All right, so the other thing that we have to think about is sometimes the body of loop contains a call to a method. So if we want to determine the order of the loop body, we have to look at the order of the method. So the method may have loops inside of it, right? So if we've got, let's say the method has a double loop and it's n squared, order n squared inside, the outer loop that's calling that method is order n, then we're going to have n cubed function, right? So we're going to throw away the overhead of the function call itself. It really doesn't matter. It depends on a lot of things, the language, the operating system, there's lots of things that could change the overhead of the call itself. It's just, it affects the k, right? It affects the constant that determines these things, but it doesn't affect the actual overall runtime. It would still be n cubed or whatever it happens to be. You really have to look at what's inside the method and see what the order of the code inside the method is. And then you multiply that times the order of the loop, and then you get the total order. Okay, so you just multiply these things inside the loops as you come out. All right, well, that's the end of that presentation, and that's the end of this chapter. There's a lot of stuff left to talk about with algorithmic analysis, and we'll definitely talk about these things. But for now, that's it. Thanks.